And our next presenter, and I'm proud to announce this presenter, Professor Sasha Kalashnikova from Ioffe Institute and ITMO University, St. Petersburg. Is both institutions very close to me personally. So I would really proud to announce this talk by Professor Kalashnikova. And Sasha, please.
Okay, so thank you very much. I hope you can see my presentation. Okay, yeah, thanks a lot, first of all, for inviting me, and it's really exciting meeting. Now I will be actually talking about very same material, which was also discussed in the previous talk. So I have a little bit strange task now. So it will be cobalt fluoride, it's antiferromagnet. And in fact, the work which I'm going to present is partly also motivated by very beautiful results, which were just shown in the previous talk. So, but in our study, we were aiming not at stabilizing some long-living magnetic ordering in the antiferromagnet, but instead we were really aiming at exploring what kind of high frequency, terahertz frequency magnetic excitations, magnetic dynamics we can achieve in antiferromagnets if we employ some coherent phonons. And this work was done in collaboration, that's continuation of the really long-term collaboration between my colleagues at Ioffe Institute and Radboud University, a group of Professor Alexei Kimmel. So, first of all, our motivation is that in antiferromagnets, people are now trying to explore different ways to excite and to control as high frequency magnetic excitations as possible. Because antiferromagnets, they are intrinsically fast. And of course, we have to learn how to excite and how to detect this very fast magnetic excitations, very high frequency magnetic excitations. And there are different approaches which are being examined at the moment. One of them is a very interesting one is when we are trying to use short laser pulses to actually perturb exchange interaction. And there were several works, successful works, which show that by this means we can excite, for example, so-called coherent two magnon modes, which are in fact one of the highest possible magnetic excitations in antiferromagnets. Alternatively, you can use another direction. You can use light, for example, to heat up the material, to perturb its anisotropy, and also it will help you to drive some magnetic dynamics. But unfortunately, typically it's a rather slower dynamics. It's typically ferromagnetic-like mode also in antiferromagnets. Another approach will be, of course, quite straightforward, but still very promising, very interesting, is to use resonant excitation, just using the magnetic field of the terahertz pulse and to resonantly drive antiferromagnetic resonance. And I think this approach was also partly mentioned in yesterday's talk by Keith Nielsen. And another approach is already quite exotic and really specific for optical excitation is to use so-called inverse magneto-optical or optomagnetic effects, where light acts as a very short pulse of the magnetic field and also can drive and excite the antiferromagnetic modes in antiferromagnets, for example, like in nickel ore. And also very recently it was shown there is some kind of an analogy to optomagnetic effects, so-called phonomagnetic effects, when some elliptically polarized optical phonons also exert some kind of effective magnetic field on magnetic system and can also drive some magnetization dynamics. So in our talk, in our work, we also tried to use phonons, but in a little bit different way. And the material which we are studying is the cobalt fluoride. So you already heard about this material. And we're interested in this material because it is a piezomagnetic material. So cobalt fluoride, just to remind you, it has cobalt ions. They are magnetic ions. They form two antiferromagnetically coupled sublattices. And cobalt fluoride has strong magnetic anisotropy, so antiferromagnetic vector is directed along the C. The near temperature is rather low, 38 Kelvin, but still it's possible to reach this temperature, of course. And this material is one of the basically classic materials for the piezomagnetic effect. And there are two, in fact, it has been demonstrated in the 60s that there are two types of the piezomagnetic effects in this material. First one appears when we apply the shear strain in the AB plane of the crystal, like is shown here, and then there are the changes in the distances between magnetic ions and surrounding fluorine ions, and then it changes the balance between crystal fields acting on this magnetic ions, and then we get, instead of compensated antiferromagnet, we get kind of a ferrimagnet. So we get non-zero magnetic moment along this C-axis, basically along the axis which is perpendicular to the plane in which we apply the strain. And as you already heard in previous talk, something like this can be realized also with light, using some nonlinear phononics and really driving some specific phonon modes. But apart from this piezomagnetic effect, which is usually referred to as a longitudinal piezomagnetic effect, there is also a transverse piezomagnetic effect. So in this effect, the shear strain, again, the shear strain should be applied, for example, in AC or in the BC plane. And then they will be tilting of the antiferromagnetic order away from the C-axis. And also because of the Georgetown interaction, there will be a certain canting of the magnetic moments of these two sublattices in the plane which is perpendicular to the plane where we apply the shear strain. So basically, if we apply the shear strain in the AC plane, we will get non-zero magnetic moment along the B direction. And vice versa, if we apply the shear strain in the BC plane, then we will get induced magnetic moment in the A direction. So this is a transverse piezomagnetic effect, and here we switch antiferromagnet into the weak ferromagnetic state. It has been realized for static shear strains. It was also quite well understood. So how can it help us if we want to reach some high frequency magnetization dynamics in this material? And here the idea was the following. If we look at the different phonon modes in this material, we can find a mode with symmetry EG, which is illustrated like this. And for example, if you look at this fluorides which surround this cobalt, in this mode, they will experience this kind of shift. So these two atoms will go down, and these two atoms will shift up. And therefore, it looks like the local surrounding of this cobalt ion will experience some kind of shear distortions. I don't want to call it strain, but it's kind of shear distortions. Very similar story happens to this cobalt ion. So therefore, it seems like we have some shear distortions, which are in a sense similar. We expect that they will have kind of similar effect on the magnetic moments of cobalt ions as just the simple shear strain applied in the AC or BC plane. So we want to get some kind of a terahertz analog of the transverse piezomagnetic effect. So just briefly, how we can analyze it. So we just applied the symmetry analysis. So basically, this is a little bit complicated expression taken from this paper, but basically this is just invariant, which shows what kind of magnetic contributions to the magnetic structure we can have. Basically, this term does describe exchange interaction. This term describes anisotropy. This is Georgetown interaction. And the most important part is this part, which describes actually the piezomagnetic effect in this material. And here, these large lambdas, these are the shear distortions. And here we just modified this expression and wrote down exactly the shear distortions for cobalt ions in this position and in this position. Then we can just find what, if we assume that there are such kind of shear distortions, what should be the magnetic structure? In particular, can we get some non-zero magnetic net magnetization in this material? And for this, we can just minimize this energy and find what is the magnetization. So for shear strain, it was shown in this old paper. We will see that there are from this analysis, indeed there is a magnetization, should be induced non-zero magnetic moment, which will be directed along the A-axis if we apply the shear strain in BC axis and vice versa. So that's all very, very known. So if we try to analyze in a similar way the shear distortions associated with this EG phonon mode, we should take into account that, for example, for this mode, which is shown here, we'll have shear distortions which are proportional to the normal coordinate of this phonon mode, but which will have different sign. For example, if it's AC distortions in the AC plane for these two surroundings of these two different cobalt ions. But at the same time, for example, for the shear distortions in the BC plane, they will have the same sign. So, and then we'll also get from the symmetry analysis that indeed such kind of mode should excitation of such kind of shear distortion. So this phonon mode should in fact induce some kind of non-zero magnetic moment along the B, for example. And also we can show that there can be also the component of magnetization along the A-axis as well. So in fact, so we expect that with this phonon mode, we should see the induced magnetic moment. But because we consider phonon mode, it means that these shear distortions, they oscillate at the frequency of this mode. We should expect that this magnetic moment will also oscillate at the very same frequency. So how should it look like in experiment? First of all, what is the frequency of this mode? This EG mode in the cobalt fluoride has rather high frequency of 7.5 terahertz. For example, it can be found from the just Raman spectra of this material. So it's very high frequency. So it seems like we should have access to high frequency magnetic dynamics. Also, what is good is that in Raman spectra, this line is very intense. It means that there is some kind of reasonably strong coupling between this mode and light. So we can expect to be able to drive this mode by light. And furthermore, interestingly, if we look carefully in literature, in like papers from 60s, we can see that there is in fact a hint that indeed there is a magnetization or magnetic moment associated with this high frequency magnetic moment associated with this phonon mode. In fact, like in the 70s, for example, infrared absorption in cobalt fluoride has been studied. And the authors of this work have shown that, in fact, below the Néel temperature, you can see the infrared absorption at the frequency of this mode. In fact, in principle, this mode is Raman active. It shouldn't be seen in the infrared absorption, but below the Néel temperature, you start to see this absorption at this frequency. Furthermore, this absorption is of magnetic dipole character. It actually means that there is some magnetic dynamics at this frequency associated with this phonon mode, which enables this magnetic dipole absorption of light at this frequency. So now let's proceed to basically to the experiment which we performed. So we took the single crystal of cobalt fluoride, and in order to drive this EG phonon mode, we used an approach which is quite well known from 80s. We just use so-called impulse simulated Raman scattering. So basically, we have in our very short laser pulse, which has a very broad spectrum, we can find pairs of photons with a frequency difference between them corresponding to the frequency of this EG phonon mode. And then we can have this kind of Raman scattering-like process, which is stimulated and coherent. And then we expect excitation of this phonon mode. That's a very well-known process. This is experiment. So we use linear polarized pump pulses. We use the sample which is cut perpendicular to the B axis. So it's AC plane. That's a rather thick sample. And what is most important, what is very important here, we use the linear polarized probe pulses, again, optical probe pulses. And we will measure the rotation of the polarization of the probe pulses as a function between time delay between optical pump pulse and our optical probe pulse. And another detail about the experiment, in principle, for this excitation of the phonon mode by optical pulses via this process, we need as short pulses as optical pulses as possible. Therefore, we decided to use the system which provides us with extremely short 8 femtosecond laser pulses. So therefore, they are very broad spectrum. In fact, it gave us some problems because it's not very stable source. But anyway, we tried to get as large amplitude of excited optical phonons as possible just by using very short laser pulses. So this is how experimental result looks like. So this rotation of the probe polarization as a function of the time delay. And these are the traces measured at low temperature, below near temperature, and above the near temperature. So we see there are some rather complicated dynamics, clearly some oscillatory contributions there. So we can take just Fourier transforms. So these are Fourier transforms at low temperature, at high temperature. So there are some features, some of them can be attributed to some optical phonons, but most important, we see a very nice line, very strong line in the Fourier spectrum, which corresponds to the frequency of this EG phonon. So therefore, we did excite this coherent optical EG phonon by our laser pulses. But we want to see some magnetization, some magnetic dynamics associated with this EG phonon. So, but at the moment we see that we observe this phonon below near temperature, above near temperature. So, if there is any hints on really high frequency magnetic dynamics there. So, for this we should understand actually how do we detect this phonon mode. And for example, if we will rotate the incoming probe polarization and measure this pump probe signals, we will see that, in fact, the amplitude of the oscillations at the frequency of this EG optical phonon mode is highly sensitive to the orientation of the probe polarization. And this can be easily understood. In fact, we detect, typically we detect this kind of EG phonon modes because they modulate crystallographic birefringence of the sample. So it can be expressed in the following way. So this normal coordinate of this EG phonon mode contributes to the modulation of the certain components of the dielectric tensor, dielectric permittivity tensor, and the proportionality coefficient here is, of course, the components of the Raman tensor associated with this mode. So then our dielectric permittivity tensor will look like this, and there are off-diagonal components which are actually oscillating at the frequency of the phonon mode. And this can be shown that when we have probe pulse, which enters our sample and propagates through this, now in static case, this probe pulse, linear polarized probe pulse, sees our sample as a birefringent crystal with fast axis, for example, horizontal, and slow axis, for example, vertical. But when we have this kind of phonon mode excited in the sample, then our probe pulse will see that this kind of fast and slow axis of the crystal kind of slightly oscillate at the frequency of the phonon mode. So and therefore why we can detect this EG optical phonon, coherent optical phonon mode in pump probe experiment. So because they modulate crystallographic birefringence, and of course when we measure crystallographic birefringence, we are extremely sensitive to the way how the probe pulse was initially polarized. And that's what we see in the experiment. So let's have a look how our signals depend on the incoming polarization of the probe pulses, and we can plot the amplitude of these oscillations at the frequency of the EG mode as a function of the incoming probe polarization. We see that mostly this dependence can be described by the sinus 2 theta function, which is really characteristic for the detection of the EG phonon mode via modulation of the crystallographic birefringence, as I just explained. But we will see that this kind of dependencies, the sin 2 theta dependencies, they are kind of shifted. This all dependence is a little bit shifted down. For example, when we perform the experiment at 10 Kelvin, and then the shift gets a little bit smaller at a bit higher temperature, and at the temperatures above the near temperature, the shift nearly disappears or becomes a little bit positive. So it means that if we try to describe this dependence of the amplitude of this oscillating signal as a function of the incoming probe polarization, we'll see there is sine to theta dependence, which is characteristic for modulation of the crystallographic birefringence by the EG phonon mode, plus some kind of polarization independent offset. And from this, we can try to again reconstruct what kind of dielectric permittivity tensor should be in order to provide such kind of polarization dependence for the probe polarization. And we will see that in order to get such kind of dependence, our dielectric permittivity tensor should have this symmetric off-diagonal components oscillating at the frequency of the EG phonon mode, which are related to crystallographic birefringence. But on top of this dielectric permittivity tensor should also have off-diagonal components which are basically imaginary, and also the anti-symmetric. And when we have such kind of contribution in a dielectric permittivity tensor, typically it means that we have magnetization or some magnetic moment so if it's AC component, that means that the magnetic moment should be along the B axis of the crystal. So it means that the presence of this kind of polarization, probe polarization independent component in our signal means that there is indeed kind of a Faraday rotation at the frequency of the EG phonon, which Faraday rotation which oscillates at the frequency of the EG phonon, and this Faraday rotation is a signature that indeed this EG phonon does induce some magnetic moment at the frequency of this phonon, and this magnetic moment is directed along the B axis of the crystal. Basically, the B axis, just to remind you, that's the axis along which we have a pump and probe pulses propagating. Just to try to confirm this, we plot this polarization amplitude of this polarization dependent component on the temperature, and we see that indeed it really decreases and disappears, vanishes somewhere nearby the near temperature of the sample. So that's exactly what we expect for the piezomagnetic effect, and we believe that it is indeed the manifestation of this terahertz piezomagnetic effect, which we're trying to find. And probably the very last note that how large is this effect? So we use optically EG coherent optical phonon. We probe it via crystallographic birefringence, and on top of this, there is some non-zero magnetic moment oscillating at the very same frequency. And we see this contribution is gives us nearly 10% or a little bit more of the total signal which we measure in experiment. So is it large effect or is it small effect? So we decided to try to compare this effect to some other laser-induced magnetic dynamics which we can reach in our we can find in our sample. So these are the again, this is a repetition of the experimental results. So this is the FFT spectra, and this is the line in the FFT spectra at the frequency of the EG phonon, and we believe that approximately 10% of the total intensity of this line is really corresponding to this terahertz piezomagnetic effect. So what else, do we see anything else magnetic in the signals? In fact, if we look at the Raman spectra, that at the frequency of 3.4 terahertz, there should be a so-called 2 megaton mode. So this is basically, this is the highest possible magnetic excitation, highest possible kind of eigenmagnetic excitation in this material. Basically, this the frequency of this 2 megaton mode is proportional to the exchange energy in the sample. And in fact, we also can try to resolve this two magnet mode in our experiment. It also can be excited optically, but we see that it seems like this two magnet mode has much smaller amplitude, at least when we probe it optically, as compared to this terahertz piezomagnetic effect. And furthermore, what is important to emphasize that because of this terahertz piezomagnetic effect, we drive the magnetic dynamics at the frequency, which is in fact much higher, almost 2 times higher than the frequency of the two magnet mode in this material. So this brings me to my conclusions that we believe that in piezomagnetic antiferromagnetic cobalt fluoride, when we excite optically coherent, e.g. optical phonon mode, there are shear distortions of the local environment of the magnetic cobalt ions, which are associated with this optical phonon mode, and these shear distortions induce non-zero magnetic moment, which also oscillates at the frequency of this phonon. So it's very high frequency, 7.45 terahertz. And interestingly, therefore, we managed to excite the magnetic dynamics at the frequencies exceeding even the frequency of two magnet mode in this material. And in the experiment, we visualized this effect via just measuring pump probe Faraday rotation. So with this, I would like to thank you for your attention, and I hope there will be questions. Thank you.
Please, questions. Thank you very much, Sasha, for great talk. And Keith, please.
Yeah, this was very interesting. So I do have a couple of questions. One is, I think did I get it right that you said that this 7.5 terahertz mode is also magnetic dipole absorbing?
Yes, that's according to the literature, to this paper. Indeed, they observed that there is infrared absorption. So if you use infrared light at this resonant with this frequency, there is a well, not very strong, but kind of magnetic dipole absorption at this at the very same frequency, and it was observed only below the near temperature.
Mm-hmm. So, So does it mean then that when you excite this mode optically, there also should be, maybe not so strong, but still should be some coherent emission at 7.5 terahertz, because of course the same effect will lead to radiation, right? I
think so. Yes, I think you're right. Yes.
Yeah.
I don't think anybody tried to do it. We didn't, but I think it's correct. Yes.
Okay. All right. Well, that's interesting for sure.
Yeah, for the emission. Matthias, please. No. Oh, it's something yellow on. Okay, I thought it's your hand. I'm sorry.
I can always come up with a question if you want.
Okay, sure. You always welcome. You have a great questions, a very great suggestions. So we always welcome your talk, your questions, your comments.
Sasha, I would like to ask a stupid question, if I may.
Sure. There was a question, right?
Yeah, okay, but then the host told me I should shut up. Okay, anyway, sorry about that. When you Raman excite an asymmetric mode, what determines the phase in which the excitation goes? Maybe I should know this, but
okay, that's a good question. Let me see. Yeah, I was thinking about this, and
or am I exciting both at the same time? I guess then.
Well, it definitely always controlled by the polarization of laser pulse, and that's That's a good question. It's a shame because I don't think I have a good answer to this question. But we clearly see that. So it should. Well, I must admit I don't have a good question. A good answer.
Could I suggest a response here? You know, it's essentially the sign of the differential polarizability.
Yes.
So there's no universal answer. It will differ from one mode to the next. You could say it this way: if you displace along the phonon coordinate, does the refractive index or the tensor element or the dielectric tensor element increase or decrease? Whichever one it is, that's what will determine the answer.
Yes, thanks a lot. Yes, I agree.
Mm-hmm.
So basically, that's that's the sign of this Raman tensor, I think.
Yeah.
Raman tensor component. Yes.
Thank you very much, Sasha. Thank you for the great talk. As I always talk, said we have a not good message. One of our presenters became sick last night and with high fever. He called and asked to be removed. So Andrea will not present.